My project is called Testing Chebyshev's Bias for Prime Numbers up to 5 times 10 to the power of 15. It is a part of a more ambitious project to test Chebyshev's bias up to 1.8 times 10 to the power of 19, that may take many years to complete. Chebyshev's bias is a phenomenon known for 165 years, and extensively researched by a number of outstanding mathematicians from all over the world. It is closely related to the generalized Riemann hypothesis, that laid the foundation of the modern number theory. In 165 years, mathematicians, mainly British and American, managed to test Chebyshev's bias numerically for primes up to 10 to the power of 12. The main goal of my project was to expand this range 5,000 times, and to test Chebyshev's bias for 15 most biased prime number races, established theoretically by 2 Canadian mathematicians in 2013. I also checked all newly found zones against theoretical predictions made over the past 20 years. In addition, I plan to make all project data, for the first time, available to all mathematicians in full by contributing them to the online encyclopedia of integer sequences, and to the repository on my website. Chebyshevv was a famous Russian mathematician who lived in the 19th century. In 1853 he wrote a famous letter to his professor and fellow mathematician Pavel Fuss, who was a grandson of Leonhard Euler. In this letter he made an interesting observation that there are more primes that are congruent to 3 modulo 4, than primes that are congruent to 1 modulo 4. Since then this conjecture has been called Chebyshev's bias. Chebyshev's letter to Fuss is still cited in each and every paper in this field. Chebyshev's bias could be easily expressed through prime counting function called prime pi. In modulo 4 case, prime pi could be divided into 2 prime pi functions with residues 3 and 1 respectively. These functions compete with each other, and this competition is often called prime number race. Chebyshevv just guessed that one of the teams always had a lead over the other. The same conjecture or Chebyshev's bias applies to other moduli and resulting prime number races. The difference in number of primes in 2 competing teams is called delta. If Chebyshevv was right, delta should always be positive. If we look at modulo 4 race delta, it seems to be the case for a long time. No negative delta had been known for over 100 years since Chebyshev's letter to Fuss. The first negative point was discovered only in 1957 at a prime number equal to 26,861. And the next one was located at 616,841, a way too far for a manual search. There has been considerable volume of works in Chebyshev's bias area over the past 165 years, as Chebyshev's conjecture became the origin of comparative prime number theory. The main ones are those of Littlewood in 1914, Knapowski and Turan in 1962, Rubinstein and Sarnak in 1994, Bayes and Hudson from 1978 to 2001, as well as Fierley and Martin in 2013. Chebyshev's bias was unexpected for mathematicians, as Dirichlet prime number theorem for arithmetic progression postulated that 2 arithmetic progressions for 2 prime number races contained infinitely many prime numbers. In 1914 Littlewood proved theoretically that Chebyshevv had been wrong, and there should always be zones with negative delta. Despite his proof, no negative zones had been known till 1957. The search for negative zones got a new impulse with the advent of computer era. Several infrequent zones were found between 1957 and 1962. To reconcile Littlewood's theorem with empirical data, Knapowski and Turan in 1962 suggested that Chebyshev's bias should be valid only asymptotically, or, in other words, in infinity. The real breakthrough happened in 1994, when Rubinstein and Sarnak proved that if generalized Riemann hypothesis was true, then Knapowski-Turan conjecture should be false. This became the missing link between Chebyshev's bias and the main hypothesis of the modern number theory. The switch to generalized Riemann hypothesis allowed mathematicians to consider Chebyshev's bias, not only as the sum over primes in arithmetic progression, but also as the sum over zeros of corresponding Dirichlet L function. Rubinstein and Sarnak also proved that the presence of a square residue among corresponding residues was the main source and the origin of Chebyshev's bias. The race with a non-square residue almost ever contained more primes than the race with a square residue. With the missing link in place, the extensive hunt for new negative zones started. Initially, empirical data supported Knupowski-Turhan conjecture, but after Bayes and Hudson research, and the discoveries of new zones above 10 to the power of 9, it became clear that it was wrong. The search for new zones had been very slow, sometimes decades passed between the discoveries. Considerable progress was made by Bayes and Hudson, especially for moduli 3, 4, and 8. By 1996 there had been 10 zones known for 3 different prime number races. The situation with moduli 12 and 24 was much worse. By 1996 there had been almost nothing known about them. The only found zone was defined only approximately. The situation has not changed much after 1996. In 2011 an American programmer Johnson found the second zone for modulo 3 race, although with some mistakes. This happened 33 years after the first zone for this race was found. In 2016 a Canadian programmer Martin discovered the first point for 1 versus 7 modulo 8 race. Though finding this point was a significant progress, it was not clear how large this zone was and where its last point was located. On the theoretical front, in 1994 Rubinstein and Sarnak also introduced the idea of logarithmic density for the corresponding prime number races. Logarithmic density simply meant the probability that one team would win over the other. They also calculated logarithmic density for the most popular cases, including modulo 4 case. The high value that they found simply meant that Chebyshev'v was right 99.59% of the time. Using this idea, 2 Canadian mathematicians Fiorelli and Martin in 2013 calculated and published logarithmic densities for 120 most biased prime number races. I selected top 15 of them for this project. When Fiorelli and Martin published their article in 2013, there had been negative zones known for only 4 races from their top 15 list. At the end of their research in 2001, Bayes and Hudson, together with Ford and Rubinstein, made a number of important theoretical predictions, based on their models where the next zones for various prime number races should be located. Some of those zones, below 10 to the power of 15, became the goal to check for this project. Very important predictions were made by Ford and Hudson for moduli 12 and 24. There should be at least 4 zones below 5 times 10 to the power of 15, the upper bound of my project. Other predicted zones were located much higher. Bayes and Hudson had stopped at 10 to the power of 12 line, because higher range was beyond the technical capabilities of that time. They did not have fast and reliable prime number generators, the databases they used demanded too much disk space, and there were no affordable servers available to work non-stop weeks and months. Only recent advances in software and hardware development made 5 times 10 to the power of 15 range possible. To achieve project goals, I developed 2 programs in C++, using results from my initial computer science project. The first one allowed to test any modulo race with 2 selected residues, whereas the second one tested only moduli below 30, but for all possible combinations of residues. Both programs used a fast real-time prime number generator called Chebyshev'v, that was selected from a number of other generators I checked. These programs allowed to test Chebyshev's bias up to 1.8 times 10 to the power of 19, much higher than the upper bound of this project. In addition, a control program was written in C# that worked with a large prime number database up to 10 to the power of 12. Using a database was about the same way that Bayes and Hudson used 20 years before. The control program was necessary to verify independently with different algorithms the correct work of the main programs. The software development and testing in my previous computer science project was finished by the end of 2017. After my software was tested and confirmed with previously known numbers below 10 to the power of 12, it was launched on 5 remote Microsoft Azure servers to expand the known range 5,000 times. Then the initial numerical calculations were completed in the beginning of 2018. For Modulo 3 race we found correctly the second zone, previously found with mistakes by Johnson in 2011. This zone matched almost exactly the prediction made by Bayes and Hudson back in 2001. In addition, in this and other races, we defined the endpoint for all zones as well as their number of terms. For the most studied Modulo 4 race, we found 3 new zones, the 8th, 9th, and 10th. Whereas the 8th zone happened a little bit lower than predicted by Bayes and Hudson, 2 other zones were not expected up to 10 to the power of 18. This early appearance requires theoretical explanation as well as revision of the models used to make the prediction. In addition, for this and other cases, we define zones not only with primes, where they happened, but also with the corresponding values of prime pi function. This has never been done before. Bayes and Hudson, as well as other researchers, always used primes for zone definition, not their count. There have been very interesting results for Modulo 8 case. First, no zones were found for 1 versus 3 Modulo 8 race. Second, the first zone for 1 versus 7 Modulo 8 race, was fully defined. Previously only one point, namely, the first one, of this zone had been known. This zone happened exactly where it was predicted. Third, out of 5 new found zones for 1 versus 5 Modulo 8 race, only 2 last zones had been predicted correctly. Theoretical models failed to predict the 3 smaller zones that occurred before the 2 larger ones. This really need theoretical explanation and possible revision of used models. The same observations are true for prime pi data. 1 versus 3 Modulo 8 race, which is number 7, on Furilli and Martin top 15 list, still has no found zones. Remember, that if generalized Riemann hypothesis is true, this race, as well as the others, must have negative zones. But the most interesting results were obtained for the moduli 12 and 24. For modulo 12, I found the first ever zones for 2 prime number races, 1 versus 5 and 1 versus 7 modulo 12. These zones were not predicted below 9.7 times 10 to the power of 16. Both zones are extremely narrow. Their early appearance requires theoretical explanation. On the other hand, I found no zone for 1 versus 11 modulo 12 race. In 2001 Ford and Hudson predicted that no such zone should occur below 10 to the power of 20. For modulo 24, no zones were found for 1 versus 5, 1 versus 7, 1 versus 11 and 1 versus 23 cases. For other races, I found 13 new zones in total, including the first ever zones for 1 versus 17 and 1 versus 19 races. These races are the number 9 and number 6 on Furilli and Martin most biased prime number races list. As you could see, some of the found zones matched predictions, but many did not. For example, for 1 versus 13 case, predictions failed to locate 3 smaller zones before the correct value for the other 2 larger ones. For modulo 24 case, 6 new sequences were registered with the online Encyclopedia of Integer Sequences. By the end of my project, for 6 prime number races out of 15 most biased prime number races tested, no negative zones were known, and modulo 24 case contains 4 of those missing 6. As Chebyshev's bias directly follows from generalized Riemann hypothesis, unless these zones are found, there is still a possibility that generalized Riemann hypothesis is wrong, or needs some revision. Let's compare the status of negative zone search for most biased prime number races in 2013, when Furilli and Martin published their list, and after the completion of my project. If in 2013 out of top 15 races, negative zones were known for only 4, now they are known for 9 races. Only top 5 and number 7, 6 in total, remain unknown. Remember that these zones need to be found to support the validity of generalized Riemann hypothesis. In addition, the upper boundary of Chebyshev's bias math research was expanded 5,000 times from 10 to the power of 12, to 5 times 10 to the power of 15. Summarizing, I found 25 new zones, including 4 first-ever zones for 4 most biased prime number races out of top 15. This is a significant progress achieved in less than a year. All found zones are included in 18 sequences, contributed to the online encyclopedia of integer sequences. For the first time, they became available in full and unabridged form, to all mathematicians working in a prime number theory field. In addition, all these 18 sequences are available at the repository on my website math101.guru. The information on the website is updated immediately, as I receive new data, whereas it may be delayed in the online encyclopedia of integer sequences. Let's make some conclusions. First, I managed to expand successfully 5,000 times, to 5 times 10 to the power of 15, the range previously tested by mathematicians. Second, my software used an innovative approach, of applying real-time prime number generator, instead of prime number databases used before. This allowed to save big on required disk space, and made considerably higher, than 10 to the power of 12 ranges possible. In fact, created programs could be used to test Chebyshev's bias up to 1.8 times 10 to the power of 19. Third, I found 25 new zones for 9 most biased prime number races, including the first ever zones for 4 races. This is significant progress in Chebyshev's bias area. All these zones are included into 18 separate sequences available online to those interested in number theory. For the first time, all zones were fully defined, including their beginning, end, and number of terms. Also, all zones were defined not only for primes, but for prime pi function as well. Finally, I found out that theoretical models, developed over the past 20 years, predicted large zones relatively well, but failed to predict small zones, that happened more often than was presumed. Therefore, these models need review and revision to accommodate project results. This project numerical results are objective, whereas theoretical models are based on some presumptions, conjectures, and hypotheses. There are still 6 races, out of top 15, where no negative zones are known. My next effort will be directed to expanding the project range by further 2,000 times, to 10 to the power of 19, and trying to find some of those remaining 6. Unless these zones are found, there is still a possibility that generalized Riemann hypothesis is wrong, or needs some revision. I am also planning to publish my results in the near future. Thanks a lot for your attention and, please, visit my math101.guru website.